Hey everybody. All right, it's so great to see so many of you trying to get in here. There's no more seats, unfortunately, but squeeze down the sides, and I'll promise to make this as comfortable as possible for you. All right, we're going to talk about writing inefficient C# code. I think we can all admit in here, at times we've written inefficient code. Hopefully today I'm going to show you some of the ways you might be writing code that is rather inefficient without realizing, easy traps that we fall into, give you a better understanding of what's actually going on under the hood when we write some of these, or use some of these friendly extension methods in our code, and then show you ultimately how to detect and solve those problems when you have issues in, say, a production application as well. So let's get started. A little bit about me. My name's Callum Whyte. You can find me on various social networks at that handle there. I'm still on Twitter for my sins. I'm a Microsoft MVP, and by trade, I'm a .NET developer. Nowadays, I run a consultancy based out of the UK. We do .NET and Azure solutions called Bump. Hence, I am the chief bumpster. I get to speak at lots of events to see awesome people like yourselves, and I organize a few of my own as well. So amongst writing code, I get to do loads of stuff in the community, which I love. So let's first touch on why efficiency actually matters in our applications. And the word efficiency is probably going to have different meanings to different people. If I've got my developer manager hat on, efficiency is how can a member of my team write or make a new feature as quickly as possible so that they can move on to something else and we can ship more code and we can bill more money to our customers. Perhaps if you're a particularly environmentally conscious organization, efficiency is using as minimal amount of compute as possible to do as much as possible. If you're, say, a financial organization, efficiency is making sure you're responding to trade requests or anything within literally milliseconds of them happening as fast as humanly possible. It means different things in different spaces as well. So if anyone can think back to the Apollo rockets, and when we sent man to the moon, those rockets had literally 1 megabyte of memory on board. I don't think there's probably anyone in this room that's working within a footprint or an envelope as small as that nowadays. We are absolutely spoilt with resources. Your laptops, or your mobile phones have got more memory in them than sent man to the moon, which is just an incredible thing to think about. So nowadays in the space of, in the .NET space, we can actually run .NET basically anywhere. With .NET Core and beyond, it's cross-platform, truly cross-platform. I've seen people running it on everything from a smartwatch all the way down to microcontrollers and doing some really, really interesting things with IoT. So everyone's definition of what's efficient and their constraints are going to differ. Of course, speed might be your primary concern, in which case you're going to be writing your code for as fast as possible execution without necessarily worrying too much about readability and maintainability. Cost is also a huge concern for a lot of people, be that compute needs, the resources involved in building those, and as I mentioned, environmental sustainability is a big aspect as well. So regardless of what your angle is to wanting to write more efficient code, there's plenty that we can do. And the best place to start is with the really small, low-hanging fruit items. You have to find your balance here, is I guess what I'm saying. As with everything in software, it depends. If you really want to go all in and write the most efficient software, be my guest. But you'll probably end up with a more unmaintainable solution. We're going to talk about the easy mistakes. This is the stuff that I see on a daily basis in my work, things that people do without necessarily realizing the impact. But first, let's talk a little bit about how .NET actually works under the hood. CLR, GIT, GC, WTF, what are all these acronyms? What do they mean? Well, so the CLR in .NET is the Common Language Runtime. This is effectively the set of tools that make your .NET application run. They are responsible for running .NET in a variety of environments, from on your local machine for developing and debugging, all the way through to in production on servers or on a phone if you're deploying onto a phone. JIT, just-in-time compiler. This is a feature of .NET because it is a compiled language. That compiler needs to run and turn your C# code that you've written into machine-understandable code that a computer, the environment that you're specifically running in, can understand. This means that there's different CPUs you're targeting. If you're building for an Intel CPU or for an ARM chip, the JIT will do different things with that C# code to make that run and execute on that chip as efficiently as possible, ideally. Finally, the garbage collector is responsible for making sure the application runs smoothly and that you don't necessarily have to worry about managing things like memory. The garbage collector's job is to make sure the memory of the application is being used as efficiently as possible. It allocates memory onto various parts of the heap and the stack and clears that out for you. So again, you don't have to worry about it. Memory management in .NET is a whole topic that, we could go into today, but you'd be here for about 3 hours, and there's far better qualified people than me to talk about it. But as a sort of very high-level overview, we have these concepts of memory management in .NET. We have the free memory. This is the memory that's available to the application for it to allocate to processing and to different tasks that you need to do. You have your reserved memory. This is memory that .NET has allocated for your application because it believes you need it, but nothing has yet been committed into that memory. There's nothing actually stored in it. So it's using space, using compute, but it's not actually doing anything with that. You then have your committed memory. This is the memory that actually has data written to it that your application is going to use. And that data is stored across 3 different, they're called generations, areas of memory. Gen 0, 1, and 2. And effectively, .NET will manage where that memory is stored based on the frequency of its use and the type of object that it actually is. So the Gen 0 heap is effectively all of your short-lived items, things that are just popped into memory quickly and then disposed of very quickly. Your Gen 1 heap is those sort of mid-term objects, and those live as sort of an intermediate between the long-lived and the short-lived objects, and then finally Gen 2 is your long-lived objects. We're talking things like statics in C# that don't disappear, or constants even. So it's really important to understand these because .NET, the garbage collector, is constantly trying to move objects between these different heaps to make sure that it can free up one of these generations. And the reason we've split it into 3 there is so that the garbage collector can clear those out easily. In theory, Gen 0 should be being cleared fairly frequently. It's stuff that doesn't need to hang around, all the way to Gen 2, which should be something that you actually need to hold on to. So this is what the garbage collector does. Its job is to clear and move objects between all of those different heaps. I like to describe the garbage collector in .NET as a tightrope walker, walking along that very fine line, and it's got a pole, and it has to balance and make sure that the application doesn't fall over, and it's using the resources it has available to it as efficiently as possible. When you compare this to unmanaged languages, like, for example, C, back in the day with C, anyone in here still writing C, maybe for fun? Or oh, whoa, a lot of you, cool. With C, C is an unmanaged language, and effectively you have to handle things like memory allocations completely yourself. .NET and the garbage collector does that for you. And it's beautiful because it means without really thinking about what we're having to do, we can new up an object and away we go. In C, you have to actually allocate the memory that you need. So with this example, I'm creating an array of integers in this case. In C, I have to specifically say I need an array and it needs 4 different items in that array. And so 4 items of memory are allocated to that array in C. In C#, we just new up an array, and amazing, away we go. But this is where things start to get dangerous, because whilst that's super easy, it also starts to introduce things this is where things start to go wrong when you have a inefficient code. The thing I see done wrong time and time and time again is collections. People misuse collections in .NET. And by collections, I'm talking about everything from an array to a list to a whole host of things. So People should be familiar, I hope, with a lot of these interface names that are on screen right now. IEnumerable. This is a lazy evaluated collection, effectively. And you have its cousin, iQueryable, which is an IEnumerable that can have querying functions built on top of it. Effectively, an IEnumerable is just a collection of things. There is no key, there's no nice, easy way to go and look it up. You have to enumerate over that collection to go and find items. You then have this iCollection concept, which is mutable. So you can add, remove, and clear things. And there's various implementations of similar things further down, like iSets, that allow you to do similar stuff, but have a lot more features. An iList, people should be familiar with the concept of lists and arrays in C#, but this allows you to do everything that a collection does, plus it has an indexer. So every item in that list has an integer-based number for its position, and you can then insert things at certain positions. The iSet is this idea of a collection, but it's unique. So hash set, sorted set, immutable set, frozen set, these are concepts in .NET that at least the former two you should be familiar with. Frozen set's fairly new. Yeah, this is already sorted, so at the time you insert an item, it will get automatically sorted and put into that collection in the right place. If it's a hash set, it makes sure that that item doesn't already exist in the collection, so on and so forth. There's a lot that goes on behind the scenes of all of these different implementations, but effectively, you can think of everything in .NET that's enumerable is an IEnumerable, and then collections, lists, sets build on top of that. Finally, we've got this fancy one at the bottom, dictionaries. Again, people are hopefully very familiar with the idea of dictionaries. It's a key, and it's a value, and it's multiple of those. Well, the way that actually works under the hood is .NET keeps a list of two things around, a list of the values and a list of the keys in a hash table. And it uses this getHashCode method divided by the count of the items in the collection to determine where in that hash table your key and value exists. So when you go and try and find an item by key or value, that is effectively what it's doing. I said value there, sorry. You can't look up items by value, but yeah, you'd have to enumerate it. Anyway, yeah, getHashCode by the count of the items. So there's math going on there, even to try and get an item out of a dictionary as efficiently as possible by its key. Yeah, so many different possible implementations here that hopefully we're familiar with, but get misused time and time again. Let's talk about enumerators. I mentioned that, in theory, everything is an IEnumerable. Everything that is a collection of many things in .NET is an IEnumerable. And we have this concept called an enumerator. An enumerator's job is to loop over your collection and find an item. This is a very, very crude example of an enumerator at its simplest form. But the idea is you have two methods on it, or three properties, a property and two methods. You go move next, you've got a reset method, and you've got the current position. The enumerator's job is to take the collection of items and to loop over that. So every time you call move next, it will increment the position, and your current property will be updated with the next item in that collection. Its job is just to find an item at its position until the very end, until there's nothing left. This is used in .NET internally for every single loop, every single enumeration. So even when you're doing like a for each or a for loop, that's effectively an enumerator in the background. You can implement your own ones of these, of course. So as I've done here, you take the IEnumerator interface, you populate these methods, and you can do whatever you want. So this doesn't have to be finding things by position. It could literally be going off and doing API calls and silly things if you really, really wanted to. But essentially, .NET ships a bunch of these by default that you don't necessarily need to worry about. These are typically buried behind friendly methods that we use maybe all the time. Any, where, count, first, last. And these are really handy because we don't have to know exactly how these collections work under the hood. We don't need to know the fact that an array has lengths, whilst lists has counts, whilst they all have different properties. These methods in .NET Core have been made significantly more efficient. However, in .NET Framework, if you were to call .any on any collection it will enumerate the entire collection, and when it finds the first item, it will bomb out and go, yep, cool, we found an item. There is any items in this collection. Similarly for count, in .NET Framework, it would loop the entire collection and count each item individually for you and tell you, hey, here is the total number of items. Well, with .NET Core, .NET 3 and beyond, of all of these all have key properties. So a iCollection has a count, an iList has a count. As I said, arrays have a length, the amount of memory allocated to them. And so these methods now in .NET Core actually go and check that. So if you're calling .any on a collection, it will first say, oh, is it an iCollection, is it an iSet, does it have a count property, and just return that value. But if it is not one of those things, if it's just a raw IEnumerable, it will still go and enumerate and check for those, go and work it out. Similarly, where, first, last, these are fairly common as well because they allow you to pass in a predicate that will filter that collection. And the only way for .NET to go and determine if that filter is true is to evaluate the items in the collection until one is true. So in this case, where will return an IEnumerable with an additional enumerator on the top, which wraps the core enumerator that was being used originally and puts that condition in place. So every time it enumerates, it first checks that condition, and if that is true, it will return it, otherwise it will continue. First and last work in a very similar way. They're doing that where under the hood, but they're just going to return the first one, or they're going to go in reverse along the collection as well. So these are probably used in 90% of the people's code in this room, chances are. Unless you're really hardcore and you're writing everything directly yourself, directly to the enumerator, chances are you're using these. But this is where it gets really dangerous. If you don't understand the actual collection that you're performing this against, you're going to have some trouble. If it is a raw IEnumerable with absolutely nothing, like a list or anything, it doesn't have any of those count or length properties, it is going to go and enumerate. So this is where, it's really important to understand exactly how these work. Let's talk quickly about array sizing. So arrays in .NET are sort of the fundamental principle of how data is stored in these collections. A list is just an array in the background. So when you call an array, when you create a new array, new int array, as I had in my example earlier, that will create you an empty object in memory with nothing allocated, zero allocations in that. So at this point, the array has a count of 0 and a capacity of 0. An array is always maintaining these two values, so there is nothing assigned, there's nothing in there. This is fairly harmless to do. But as soon as we start adding values in, an array, you can see how it gets quite expensive. I've changed this out to be Portuguese wine regions. This was a beer example before. I'm using different wine regions for this example. But I've created an array, and I've put each letter of that wine region, DAO, I guess, into the array. So at this point, my array has a count of 3 items, 3 letters for DAO, but it has a capacity of 4. We have this extra item on the end here. And this is because the arrays are effectively allocated in quads, in 4s. And so as soon as we then add a 4th letter, that's filled up the array. If we want to add a 5th letter, it needs to add another 4, or effectively double in size. So we've got Douro here, which is the local wine region. And because that's now 5 letters here, it's had to add the additional 4 empty slots. And it's filled one of those with the O. So in this case, an array has now actually created 8 items of memory for 5 letters. Where before we could have done new array and actually specified the size, like in C, we know it's going to be 5 letters. .NET now is starting to allocate more memory than potentially it needs just for your exact purpose. And this can get even worse. In this case, we've got Atlantico, which is a 9-letter word. And of course, that's 1 more than 8, and it's added another 8 on the top. This can get really bad. If you've got an array that's 256 items and you add a 257th item, you've now got an array that is 512 spaces. It's allocated far more memory than it actually needs. So there's an argument here for making sure that you size your arrays properly initially. Equally, I mentioned that lists are backed by an array under the hood. We love lists in .NET. We love ToList as a nice friendly extension method where we can just easily add new items to these collections. Unfortunately, what that means is it's building an array underneath for you. And if you add an item that's going to mean the array needs to be resized and add more space to the array, well, it's going to create an even bigger array in the background. It's just going to keep growing and growing and growing. So you have to be a little mindful of that. ToArray is a similar method. So this allows you to create a brand new array of T, of type, and what that will do is if you call that on any enumerable, IEnumerable, it will copy every single item out of that IEnumerable. It will enumerate it, copy each item into the new array that's been created. But that array, depending on what you copied from, will either be completely dynamically assessed or will be actually the exact size you need. So if I have a list of items that's got 7 items in it, and that has a count property, .NET will go, okay, it's got a count property, and there's only 7 items in there, so when you're calling ToArray, we know you only need an array of 7 items. And so it's going to create an array with just 7 items, nothing spare, nothing more, nothing less. That's really cool. But if you do that on an IEnumerable, where it doesn't have that count property, doesn't have a length property, it doesn't know how big that's going to be. So it's going to enumerate, and each time you need to add a new item, it's going to say, I need to expand my array even more. And you're going to end up with an array that's oversized for what you probably intended. So the long and short of it is, if you know the count, you're better off creating an array up front with the exact size that you need. Same thing applies to list. As I said, the ToList is backed by a list is backed by an array. It will enumerate and then copy the items. If it's already a list, thankfully it's not going to do that, which is really handy now. However, in .NET Framework, it certainly did. Add, insert. So these will do a similar operation where they will work out the position that it needs to add your item to. When you're calling add, it's going to get the count, the current length of that array. It's going to add 1 and going to insert that at that position. If that position doesn't exist, it's got to double the capacity of the underlying array. Same with insert. Insert is actually going to completely resize your array every time you do an insert. So it's going to say, I have 12 items, I need to add a 13th item. It's going to create a brand new array under the hood. It's going to copy each of those items at all of the relevant positions in, insert your new one at the position you've desired, and then copy the remaining items. Fairly inefficient as well. If you can avoid it, add and insert are, inefficient. I come back to this. If we know the size of the array up front, this is really efficient. If we don't, there's some work to go and work it out. Be mindful of this. People do this time and time again and get it wrong. Okay, I've got some code demos, which should make this a bit more fun. Some of these are, sample, lab, made-up code. Some of it is actual code that I've seen on pull requests and things recently, and it made me scream. But, it's real. So, I have this enumeration demo. Let's jump to my code here. So, can people at the back vaguely see the code? Zoom a bit more? Yeah, we can zoom a bit more. 200%. Is that okay? Bit more? No? Fine. Okay, we'll stick with that. So, .NET has this new concept in, I think it was .NET 8, where you can add these expression operators, which are really nice. So when you create a IEnumerable of object, you can say that equals this kind of square bracket syntax. And .NET will then automatically work out what type this should actually be under the hood. Previously, you would have had to go, okay, IEnumerable object equals a new list or a new array. But .NET's going to decide it for you at this point. So before I run the code, anyone want to take a guess what this is actually going to be, what underlying type .NET's going to give me? And just shout it out. An array. Cool. It is an array. And it's going to be an array of 0 items. It's effectively, No real footprint of doing this. What about this? So I've got an I list of objects. Any guesses what this is going to be? A list, yeah, awesome. And then we've got this idea here of an I collection. What might an I collection generate? A list? Yeah, it's a list as well. And at some point we're going to get this for dictionaries too. There's a discussion about it right now about kind of dictionary expression operators where it will be able to do things, yeah, fancy things for you. Hash sets work, etc. So all of the different types actually work here. You can just use the syntax. This is great because it means that .NET's going to automatically create an appropriate option for you, potentially, if you really don't know what's going to go into this collection. And then, of course, you can call your ToList and whatever other methods on here that become slightly inefficient. So calling the expression operator on IEnumerable and then ToList is going to create a new list and copy the items in. There are 0 items in this case, so it's going to be nothing, but if there was 3, 4, 5 items in there, like I can do up here, I can just put 1, 2, 3. That's now going to allocate an array with 3 items in it, and then going to create a new array to create the list and copy 3 items in it. But that array is actually going to have 4 items, and starts to get really inefficient. I said I was going to show you some code that I saw in a pull request recently. Nobody scream. This is a genuine piece of code that I saw in a pull request. And in fact, to be nice, I've put the collection expression in there. But effectively, this is someone newing up a collection. They are then checking if there was any items in that collection, then making sure that the count was greater than 0. And then, once that's good, they're going to go through and make sure that there is, it's going to get a list of the items in there where the value is not null, and it's going to turn that into a list, then it's going to iterate over that, and then it's going to null check the items again, just for safe measure. No word of a lie, this was in a project I saw. Okay, this is ridiculously inefficient for so many reasons. First things first, .any is going to enumerate that collection and check that there are items in there. Thankfully, because we're using the expression operator, it's going to create an array. And an array has that length property, and so it knows that if the length is more than 0, yes, there is an item. But if it wasn't, perhaps this is coming from some other library, some API you're using, well, that could be just a raw IEnumerable. Never trust it, basically. If it's IEnumerable, assume that it will enumerate. Count is also then going to enumerate, but it's going to enumerate every single item just to check and make sure that, yes, there is items. And then, yeah, make sure that's greater than 0. It's doing the exact same thing as the .any. Then we come down to our next line where we've got our collection where clause. That is going to enumerate again and filter every single item and make sure that those values are not null. And then finally, just as a nice punch in the gut, it's going to enumerate once more and get all those items out of the IEnumerable that's been created by where to create a list, and then allocate a bunch of memory to do it. Oh, and then we loop again, and then we null check again. Come on, this is ridiculous. So how would we make this code slightly more efficient? I have an example here. Following the Portuguese wines theme, I've created a wines collection. This is an object that I've created, and it's just got some hard-coded values in there. You can see up here we've got wines, it's got a couple of null values, port, Aruda, etc. I've also then implemented my own enumerator here. This is a completely contrived example that you should never do in the real world, but what it's doing is every time it enumerates, it's going to create a random subset of that list and return that to you as the item that you should be enumerating over. Meaning, in reality, every time you enumerate wine collection, it's going to give you a different list of items. This is really to simulate what might happen if you were getting that data from an API or getting it from some other library. Back to my code over here. I'm then doing my any call. And to make this a bit more efficient, I'm doing that check up front, because before, the code would enumerate and then check again if there was values in it that we actually wanted. So doing that null check up front means that we can, make sure we're only going to perform our code if it's required. We are then doing a count. Okay, that's still inefficient. And then we are still filtering it again. Okay, that's not ideal. So let's make this work a bit better. We've got our wines collection at the top. What if we were to just move this entire line out? Crazy idea. And then instead of using wines here, we can use use the items, which is the list, and count, use items here as well. This is so much better because, we don't even need this anymore either, do we? We've done all the work up front. We've done the work to take our collection, to filter it, turn it into a list. It doesn't actually need to be a list even. And then our any and our count are going to just use the properties that are on the list, the count property. Not doing any extra work here. We don't need the null check anymore either. We've already said we don't need the count. So this can literally go from being like 5 lines of code to 3 lines of code. And look at that, that's beautiful. Just to show you this running in real life and prove my point so you can believe what I'm saying, we'll actually put a breakpoint on this, and I'll show you just how many times that random enumerator gets hit. So let's pull up the wine collection on this side. I'm just going to stick it here, and I'll pop a breakpoint on there, and on there, and on there. Why not? And here, sure. So when I run this demo, it's going to run my my wines code, and you'll start to see it looping, and just see how many times it then hits the enumerator. Okay, we've hit our code. The first thing it's got to do is check if there's any items. Based on what we've established already, we believe that any is going to only enumerate once, because it's going to check that there is one item. And if one item's returned, fantastic, away we go. So click continue, we hit it once, and then we're skipping to the next line. So that's awesome. Then when we do the count, in theory, it's going to enumerate for every single item in that collection. Just pop a breakpoint there too, just to be sure. Okay. Maybe only one was returned in that time, due to my randomized code. And then when we do this where and our ToList, it's got to enumerate each item again. And then we loop, it's got to get each item again. So it's hitting it multiple times. If we optimize that code back to what we'd sort of suggested it could be, we pull our list of items out, pop them up here. We remove our any check there. We remove our count, and we can remove the null check just for safe measure. Boop. Fantastic. Run that again. We should this time only see our enumerator hit basically one time. Wines. Yeah, there we go. Thank you, pair programming session. You are correct. This should be items. So yeah, it was hit more than once there. But this time it should literally only get hit once at the time that ToList is called, and then never again. We've moved the same code, it's doing the exact same thing, we've just shuffled it around. And all of a sudden, our code is doing far, far less work. What was 10, 12 iterations before is now a single iteration. This makes a huge difference in the real world. If we're talking about efficiency, really, the goal here is just do less work. And maybe do less work faster, but we're going to come to that in a second. So there's a few optimizations that you can do in code when using, I'm going to call them these lazy, friendly extension methods. If you're doing a ToList on an item, just check if it's a list already, for God's sake. Like, if it's already a list, it's going to go and do, you don't need to go and do all of that work of copying items in and creating a new list. ToList is going to create a new list unnecessarily, potentially. So if you're dealing with an IEnumerable, just check if it's an iList first. Put your filtering up front. So where you're doing those where clauses, rather than doing an any check with a predicate in there and filtering your results, do that first and then call any on the result of that enumeration. Things like element at or indexes, where you're working with a list and you already know the position of the item, use the position. The index is a really, really efficient way in memory of getting to a specific point. Yeah, otherwise you've got to enumerate the whole thing again. This will literally just skip to the specific position, if you've got the index, that is. Also, add range. This is really interesting. So when you're adding items to a list, calling add, as I said before, is going to add, it's going to expand that array, and it's going to add more and more and more slots to make sure that there is enough space for the items you're trying to add or potentially will add in future. Whereas add range is actually going to do a bit of optimization up front. What they do is they work out the number of items that you're trying to add and the number of items currently in the collection, and it will resize the array to the exact capacity that is needed. So add range, really simple change. Rather than looping over your items to add new items, just add them all in one go. Way more efficient. Okay, we can talk about some other things. I said do less work, but the other thing is maybe do more work in parallel. We can use the same amount of compute to actually achieve similar results, but with potentially huge, vastly different outputs. So parallel, async, await. .NET has got some fantastic different paradigms of building your applications. You can do parallel processing, where on the same thread it will try and do multiple things. Async allows code to be executed across multiple different threads simultaneously, and you can then await that result. Overall, you should see a vastly improved throughput of your application. So let's just close out this demo and jump to my parallel demo. Oops. There we go, that's better. Okay, so I've got a couple of very simple demos here. Remember that wine collection from a moment ago? Well, I've created a wine service, of course. And that service's job is just to return a list of wines. It's not doing anything special. But in this case, my for loop here is going to loop over 10 times, and it's going to call that wine service and get a count of the wines each time. It's going to do that 10 times in sequence. So with the same amount of time, we're able to process 10 items. I will run that demo now, just so you can see what I mean. Oops. Let's take that off. Cool. So you can see here, it's just slowly counting through and finding the wines. Because it's newing up a new version of that service every single time it does this, the count is ever so slightly different. I don't know if people at the back can see that, but the first one returned 5 wines, the second one 3, 3, 3, 3, 3, 3, 3, 5, 3, 5, 3. It's alternating between the different counts because the logic of that service is to differ the amount of wines that are returned each time. So yeah, it's just done those slowly in parallel. Takes a second or so to actually do this. Oh, and just to simulate a real-world scenario, this has a thread sleep of a second in there. So you can imagine that's a network call or something. You're just waiting a second between each call. When we come to our async code, we're still going to new up a copy of that service each time, and these async methods still also do a thread sleep. A task delay is the async equivalent of a thread sleep. But what this should mean is, if I take these off, as soon as I call await, it's going to start processing other code, and then it's going to come back to the result of this when that's been processed. So whilst they both wait for a second, the results should come through in more or less the same amount of time because we're just waiting on the execution to happen and then waiting for the result later. So I'm going to pin this to the side just so we can hopefully see it in real time happening. If I click continue, it's going to do... Oh no, okay, whatever. Came back with 2 different counts of wines. Only twice there. That could be 10, just like before. Final option here is using parallel in .NET. So parallel is a nice feature that allows us to run the same amount of code, but on multiple different threads simultaneously. This time it's going to go and call this service 50 times. And you can start to see, whilst these were more slower and waiting for a second each time, these will still wait for a second, but they're going to wait for a second on many different threads. So as this happens, you'll start to see results come in sort of sporadically throughout that time, with all different things being computed here too. So if you're trying to do a big batch task, processing lots of data, that's actually a really great way to go. You're not waiting for that 1 second each time. It's going to wait for a second on every thread independently of each other and aggregate the results for you. So if you don't care about order, those sorts of things, parallel is a great way to do it. Lifetimes and disposal. People should be familiar with the idea that a static class in .NET lives basically for the lifetime of the application or until it's disposed of. Well, when we're doing things like dependency injection, people seem to forget about all of this sort of thing. .NET has, out of the box, 3 concepts for dependency injection. Things like transient, things like scoped, and things like singleton. So you really need to think about what your classes are doing when you inject them places. And also, when you create new instances of classes, what the lifetime of that class is. Does it get disposed of automatically? Is it holding on to data in the background that you don't necessarily know about? So in my example over here, if we jump to my lifetimes demo, I've set up exactly that same thing. My data, as you've seen it up till now, keeps trying to open things in another window. Lifetimes, there we go. My data, as you've seen up till now, is completely randomized every single time that we call that service. It's completely new data, which is fun, because what it means is, if we do inject my wine service as a transient class, it will create a new instance of that every time we try and use it, and then it will create a new collection of those items as well every single time. It's doing a lot of work each time that we don't necessarily need. Same demo as before, looping 10 times over this class, and what we should see is it comes back with 10 completely different results. So 4, 5, 4, you get the idea. But if we change that to be a singleton class, it's going to create one instance, and it's going to keep a copy of those items in memory around for a little while. It's unpinned itself. 4, 4, 4. And here it's just returning the exact same result every single time. If your service is doing something like going and fetching data from an API, and you only need to do that once up front, make it singleton. It shouldn't need to be created, there shouldn't need to be a new instance of it created each time. You shouldn't need to get that data every single time. This would be the equivalent as well of me turning my collection into a static collection. That gets put on the Gen 2 heap and then kept around. Something else I see done wrong time and time again by people is using things like memory caches wrong. Visual Studio's decided to go to sleep. No, there we go. Yeah, people using memory caches wrong is something I see a lot. In this case, I've created an instance of the memory cache. This will just store some data in memory. I've then got my wine service, and I'm making sure that I write that data straight into memory. And so I can read that value out of memory going forward, which is cool, except this is not actually what's happening at all. Here I'm writing an IEnumerable to memory. And an IEnumerable, if you remember from before, is a lazy evaluated collection. So this is just storing an instruction in memory to say, here's how you go and get that data. It's not actually got the data at this point. So realistically, you need to evaluate this data before you write it into memory. The same would be, a lot of these methods allow you to pass in like a func. I see this done all the time, where people cache the result of a func. All you're doing there is caching the instruction of how to call that code. It's not doing anything for you. It's just going to go and call that every single time you get it out of the cache. So to show this, hopefully we can chuck our breakpoint back on our collection, which is over here. And what we'd expect to see is that every time we loop over this, I'll just make that transient again. Every time we loop over this collection, we should expect to see that enumerator gets called. So the same code is actually getting called each time. I'll pin it over here again. So you can see there, it's getting called every single time we loop. However, if we change this code slightly, there we go. If we change this code slightly that we had before and make it so that we're just caching, say, the array itself, actually turning it into a physical array, we'll see that get called once the first time, and then hopefully never again. What was that? You might be right. Yes, you're right. Thank you. Anyway, so yes, you need to make sure that this value is basically being written into the memory cache and not the result, or not the function call that you want to do. I've seen this cause huge performance problems in real production systems, where it's impossible, seemingly, to work out what's going on because you're getting the data you expect, you're seeing the services that you expect to be called get called. They're just getting called far too frequently. Again, doing more work than we want to do, and yeah, ending up with slightly inefficient code. Okay, I've showed you some of the ways we can inadvertently introduce inefficient code into our applications. Now let's talk about what we can do to avoid them and the processes in which you can make some differences in your team. Firstly, benchmarking. Benchmarking is a hugely valuable tool. If you don't know if one way of doing something is more efficient than the other, because it will really depend on your case, the libraries you're working with, etc., you should benchmark it. Benchmark.net is a unbelievably powerful library that lets you do benchmarking directly in .NET. And this is great because if you're ever unsure of, if something's fast or not, you can very quickly, 2-3 lines of code, write a test that will tell you if it's fast or not. Similarly, if you've got internal applications that you're building and you want to make sure that, that your code is performant and remaining performant over time, you can write benchmark.net tests that say run in your CI pipeline and report and say, actually, at this commit, you've introduced a change that meant this code that was super efficient before is now taking 10 times as long. You can write specific tests around that. I have another demo. So, benchmark.net here. Let's fire up our example. Benchmarks. You install it as a NuGet package, and I'm now really interested in learning whether comparing the string builder in .NET to concatenate the words hello and world together is faster than using string concat, or just raw concatenation, or even string format, or string join, or string interpolation. There's all these different ways of doing this exact same problem in .NET. And yeah, anyone want to take a guess at what's faster? What's the fastest approach here? Okay. I think there was a few murmurs there, some mixed ideas though. In theory, Microsoft should be making their new nice ways of doing things as optimized as possible. I think the reality is the string builder in this case is still the most efficient, even though it's the most verbose, which is slightly crazy to think. But the point still stands. What I've done here is I've created a class, I've decorated it with an attribute that says, this is the test I want you to run. And it's going to go and run 3 instances, 10 times, and then aggregate the results. And it will just call each of these functions and test how long they took to run. Similarly, down here, I've got another test that does benchmarking of nulls and null checking. So here we're checking if the value is null, if the value does not equal null, using the is check to check if it's, to do a type check, an is not check, is null check, is not null. Anyone have any guesses at what might be the most effective, fastest way of checking for null in .NET nowadays? I think it's equal. Someone else? Is? Yeah, so we'll run the tests and find out, because I don't want to spoil things too much. But we tell our benchmark runner, here's our tests, and we click run. So I've just got to switch this to release mode, because it's a fairer test, and benchmark.net will scream at me otherwise. And what you're going to start to see here is it's going to run through all of those benchmarks that I've actually registered. And it's going to test this on a number of different potential configurations. It's testing each operation 10 times. It's doing that on 3 different instances for each of those classes, just to get a fair result. There was a result up there, if I can scroll up and get to it. Fantastic. So we've got our result. Oh, okay. Should have put a breakpoint. Never mind. It gives us a little table of our results. You can imagine that can be output into your build outputs in your CI server. You can store that somewhere, and it can be very helpful. What was the result here? Let's see. Okay, so is was 60 nanoseconds. Is not was 50 nanoseconds. Is null is not null. So it looks like the is checks are significantly more efficient than doing the equals check in .NET. So that's a great way to learn. And of course, a very simple basic example of something that is... Thank you, I did. Yes, I did. Thank you, yes, I did. Yes, so really we should be looking at the mean column here, and in this case, I mean, it's approximately still the same thing. But anyway, yeah, you get a nice little table output of the different results. Let's say you've got a performance problem in production. Let's say you've got all your benchmarks in there, and actually it's got to production, and you're now having some issues. There's some great tools by the teams at Redgate and the teams at JetBrains that have made some fantastic tools for you to profile your applications. Ant's Memory Profiler and Ant's Performance Profiler, also .memory and .trace, really interesting tools that let you get into exactly why your application is running inefficiently. That could be code being executed more than you expect. It could be an unnecessary large number of allocations. This allows you to literally peek directly at all of the data that's stored on all of your various heaps to see exactly what's happening there. Microsoft also has a really fantastic tool that is not pretty, but it works really well. And I've needed to diagnose production issues with excessive memory usage. And here you can basically see the garbage collector in action. You've got your Gen 0, 1, and 2 counts. This is just telling you the number of bytes that are in each of those heaps. And you should start to see these numbers over time slowly increase and then decrease, increase and decrease. If one of these is excessively increasing, then it's pretty obvious you've got an issue. This tool that I'm showing you here is called .NET Counters. You can download it from Microsoft Learn, and it effectively just gives you the metrics for the process that you've got running. You've then got another tool called .NET Dump, which allows you to export a memory dump of your application running in production. And you can pull this into even Visual Studio and see this directly in, drill into exactly what data is being stored there. And finally, you've got .NET Trace, which you can open in a trace viewer tool and see exactly where your code is, which code's being called and what data is being stored and exactly the values. In this case, this screenshot is actually from a site of ours where a bunch of IDs were being stored in memory and not sort of let go of. But yeah, these three tools on the side, invaluable. Not friendly, but really, really good. And you can get a really nice idea, just like this, of how your application is actually performing. If you suspect you have a memory leak, this will tell you within a couple of seconds, because you'll see that number ever increasing. I should give a shout out as well to some of these amazing off-the-shelf tools, commercial tools even, that do this actively for your application. So if you've got an application running in, say, Azure, you've got Application Insights, which has really good memory profiling tools that most people probably don't touch and probably haven't seen. Equally, if you're using Datadog, Datadog's got some fantastic tools as well, and some people I'm going to talk about in a couple of moments actively work on Datadog, doing awesome work around .NET memory profiling and enhancements. Okay, so this is what it's all accumulating to, really. The billion-row challenge. Anyone in the room gave this a go, or at least heard of it? A couple of people, nice. So the billion-row challenge is a challenge that actually spawned, I think, out of the Java community. And the idea was you have a text file with 1 billion rows in that text file. And the text data is all names of weather stations and values that they have read for temperatures. And what you need to do is write the most efficient code possible to read in that text file to calculate the averages for each of those weather stations and then return the result sorted alphabetically. Each file, the single file contains the list of weather stations. They are separated, the readings are separated by a semicolon. You need to return the min, the max, and the mean values for each of those stations and return that in an alphabetical order. So I flexed my Linq muscles and decided to write the friendliest version of this I possibly could. In this case, this is, at the top, reading in my records.txt. It synchronously reads every single line, and that takes a fair amount of time. It then splits all of the lines by something, so I end up with a list there, or an IEnumerable of string arrays. I then create a lookup in Linq. I use a function there to effectively parse the readings out as integers and store those values, and then I loop over it finally, that whole lookup, and I output the result that I want written to the console in the end, and then I, at the end, just alphabetize it. This is not the way to do it. This took about 6 minutes to run on my very, very powerful MacBook, and is certainly not what you'd want to do. However, some far smarter people than me have given this a go, and our friend Mark Rendell, who's here, he's speaking this week, has also had a go at this, and he's created some fantastic results, and they're all open on his GitHub. I should just show you first. This is his first result. It took 2 minutes and 2 seconds, basically, to execute. And down here, he's got a billion rows being executed in 5 seconds. The exact same data list, the exact same file, but he has optimized the code. Now, this shows you possibly the lengths of which Mark has gone to. He's got a graveyard here of all of his different attempts, and there's a lot of code written here, a lot of code. When we dive into the program, you'll see it's fairly straightforward, but what he's actually ended up doing is creating his own file reader, his own, like memory things. Like it's really, really crazy. So you can see in here he's doing things with pointers, and it starts to get slightly excessive. But that's what's involved in if you really want to get your code down from 2 minutes to 5 seconds. If you're building a financial trading platform, this is the kind of optimization that you do, and you end up writing less friendly code, but the trade-off is far, far more efficient and performant in this case. Mark also ran this on a MacBook, so similar to my benchmark, 5 minutes, 2 minutes, 5 seconds. Really impressive. There's a whole bunch of people who have got it even less than this, people doing things in like Rust that have managed to get it down to like half a second or something insane. But yeah, people have had a lot of fun with this. Okay, I'm going to give you some homework if that's all right. Firstly, Daniel, he is doing a talk tomorrow about benchmarking specifically, and he's going to go really deep into that. If benchmarking and profiling your applications is something you're interested in, I highly recommend checking out Daniel's session. We were chatting before this, and I think it's going to be very, very insightful. Secondly, so Kevin Gross and Christoph Nassar, they work with Datadog, and they are some incredibly smart people working on .NET performance. But this book by Konrad Kokoza, on the left-hand side here, is effectively the Bible of .NET performance. And when I say the Bible, it's about this thick as well. It's huge. There is a second edition coming out very soon, and it's a bit thinner. And he's collaborated with Kevin and Christoph to make the best pro.NET memory management book of tips and tricks. So if you're really interested in optimizing memory, go and get this book, first edition or the second one that's coming out soon. Additionally, pro.NET benchmarking, this is actually written by the author of benchmark.net. He's created a wonderful book on how you would benchmark your applications as well. A bit thinner, that one. Highly recommend this book too. So if you're interested in reading up more on these and actually implementing some of these at a larger scale, perhaps in, say, a financial environment, these books are what you need to rely on. And with that, I'm nearly out of time. Thank you very much, everybody. The code I've showed you today is on my GitHub. I'm on Twitter, and enjoy the rest of the event.